Welcome and thank you for coming to my talk on fractals as a bridge between human vision and neuromorphic computing. I'd like to discuss a practical application of this topic using a contemporary published paper as a foundation. But first, a little bit about myself. I'm the founder of a hardware and software AI consulting firm here based in Australia. I'm also an honorary member and graduate of the Computational Neurosurgery Lab at Macquarie University. I'm also a graduate of Carnegie Mellon's Software Engineering School and performed my master's thesis with the Carnegie Mellon Robotics Institute. However, just to be clear, I'm not a clinician or a biologist. The term neuromorphic computing describes an architecture where systems emulate the brain in three key areas. Firstly, that signals are driven by events rather than continuous activations. Secondly, that the system is energy efficient or lazy. And finally, that things are usually performed at the same time, as much as possible, rather than one after the other. With this definition in mind, we can see where neuromorphic computing has a great deal of potential in increasing robustness and efficiency in sensing systems. Indeed, this can be best understood in the context of visual systems, which is the most widely studied parts of the brain. This presentation proposes that fractals can be a useful tool in facilitating the emulation of human perception by assisting in the measuring and filtering of complexity in the machine vision process. We can begin by demonstrating what Nørretranders describes as the user illusion. If you put your thumb up at arm's length and look at your thumbnail, you can plainly see that this is the true limit of your actual human visual acuity. You can barely see the entirety of your thumbnail at once. The illusion pertains to your perception that you are viewing the entirety of your visual field. Indeed, the entirety of the visual field, if described as digital bits of information, is 1 billion bits per second. Though as that information steps through the various filters in the brain's visual field, it's reduced to barely 10 to 60 bits, accessible to the brain's awareness mechanisms. Traditional machine vision processing, on the other hand, is quite different. It performs visual processing equally, per bit of information, uniformly over the entire field. The only way to reduce the filter is to reduce the field, as demonstrated here with the reduction in the number of pixels. Technology has provided a brute force approach to image processing where a wide bandwidth is supplied through almost the entire visual processing pathway. Though, interestingly, in convolutional neural networking, this filtering is somewhat demonstrated as visual details are reduced in each layer until an inference is made using the supplied labels. For example, with ResNet, an inference of 1,000 labels equates to about 10 bits of decision entropy, or log 2n, with n being the 1,000 choices in the labels. But what if we could cross-pollinate machine with human vision? Gunter and others proposed a foveated vision technique where image processing is computed more heavily in the center of a region of interest, and it's reduced as it moves to the periphery. This was originally introduced to increase performance in virtual reality applications because users would not notice the reduction of quality rendered in the periphery of their foveated field of view because they had eye tracking built into the VR headsets. However, increasing computational processing in a foveated region of interest was shown to be a driving force in elevating machine vision, as demonstrated by Chung and others in 2025. By filtering and shifting attention from passive and uniform image processing to task-relevant foveated regions, an increase in performance was seen in vision processing tasks. However, how does the robot's vision scan during periods of inattention or search? This is where the fractal dimension can be quite useful. In a paper by Newport and others, the fractal dimension was shown to be a demonstrator of visual outliers. This means that with one measurement, an entire gaze pattern can be deemed unusual by comparing it to others. In this study, visual search was performed by a group of participants looking at a stimulus. Empirically, we can see that if each of these fixation points is where a participant pauses to look at a feature, the high and low complexity maps do indeed appear unusual. In a plot of all the participant fractal dimensions, we can see that they gravitate around a mean and mostly fall between two standard deviations. This hints at the likelihood of a physiological average gaze fractal dimension. This means that in the previous paper, where the robot is emulating human foveated vision, we can augment their visual search with a fractal dimension-driven saccade. Let's see how we could perform this with pseudocode. We can approximate the fractal dimension of human visual saccades to 1.5 for this demonstration, and to keep things simple, we can keep the gaze length for each step uniform. In this code sample, after setting the parameters, we can sample a random value from a normal distribution using a pseudo-Gaussian noise function, and then multiply it by I to the negative h to introduce a fractal dimension of 1.5 correlation. Finally, we clamp the results to a boundary, which can be a simulation of our visual field, for example. This code does not introduce important visual effects like inhibition of return, or anisotropic effects, or Gestalt grouping principles, contrast adaptation, visual attraction mechanisms, and many others. But this could be grounds for future work. However, this presentation does show that fractals can be used to adapt current methods, including the paper that we talked about, to be more human-like, and that those methods can easily assist in scaling machine vision to be more performant. Thank you very much.